Okay, here I will try to show the geometric intuition of the Hausdorff transformation in a bit different way. So it's similar to the first video that I showed, but it's not exactly the same thing. So for that, first recall that the scalar product of two vectors A and B can be written in matrix form with A transpose B or B transpose A, because it's symmetric, and that we know that the norm of A of a given vector squared, here it's A, is equal to the scalar product, so it is equal to A transpose A in matrix notation. Now let's redraw our reflection. So we have for vector A and our vector B. We have some unit vector V here on this axis, and here we have the vector F times V, where F is scalar. Remember that this axis and this vector, they are parallel. Okay. And now remember that V is a unit vector, so its norm is 1. And we know that the reflection, so here there is the reflection axis, so the vector A is reflected and across this reflection axis and becomes B. Remember that the reflection preserves the norm of a vector, so A and B have the same norm, the same length, because it's just the reflection. And so here we know that the vector A is equal to the vector B plus the vector F times V. So we know that B is equal to vector A minus F times V. Okay? But we know that the norm of the two vectors are equal. So we also know that their norm, so their length squared, is equal. And now we can substitute for B. Instead of B, we can write A minus F times V. So the norm of A minus F times V squared. And we can write it with matrix notation. This is A minus F times V transpose times A minus F times V. Okay? So this is equal to A transpose A minus F times A transpose V minus F times V transpose A plus F squared V transpose V. Okay? Now this is equal to the length of A squared minus 2 times F V transpose A plus f squared. So remember that the dot product of a unit vector with itself, it gives its magnitude squared, but the magnitude of a unit vector is 1. So v transpose v here will give 1, and so here this v transpose v, it's basically it's times 1, okay? And the A transpose V and the V transpose A, remember that's the same thing. It's basically it's dot product. It's the dot product in matrix form of the vector A and the vector V, and we know it's symmetric. So we know that A transpose V is equal to V transpose A. Okay, so we can rearrange that, and so we can subtract 2 times V transpose A times F. Okay? And so we can solve for F. So remember that all that is equal to the length of A squared. Remember, it comes from here. So we just substituted B. So we can subtract the norm of A squared on both sides. So we get that F squared minus 2F V transpose A equals to 0. We can put the 2F V transpose A on the other side and divide by F. So we get that F is equal to 2V transpose A. Okay? So this is F. Now, what we can do is so just to be a bit more precise, this here is when you go from is if we reflect from A and that we land on B, we could begin with the vector B and reflect around the axis to get A. This, if this is the case, F, it will be the same thing. It will just be the negative one, because we do the inverse. Basically, we go back. Okay. So this is if you start from B. Start from B. Here we start from A. Okay, it's the same things. Now we know that F is equal to 2V transpose A, and we know that we can express B. We know that. Remember, we know that A is equal to B plus V times F. So we know that B is equal to A minus V times F. Now we can substitute F, get B is equal to A minus V times 2V transpose A. Okay? So it's F. And A is a vector. So we can put the identity matrix before it. Okay, you can multiply it by the identity matrix. It won't change anything. It's like if you multiply by 1. Remember. And we can rearrange the second part. We can take the 2 in front, then times V transpose A. Okay, and then we can take out the A. And so remember that B is basically if you apply a given reflection. We can call it Q, we can call it H, also H for householder. Here maybe we will call it H. It's this reflection applied to A. We know that this is equal to this thing here. So if we divide by A on both sides, remember that it's B here. So we know that B equals to H times A, it's equal to A times the identity matrix minus 2 times B V transpose, okay? So if we divide by A on both sides, we get that our matrix H could be called Q, as we did in our first video, is equal to the identity matrix minus 2 times V transpose, okay? So this is another way to find the formula for the Hausdorff transformation. So again, it's just basic geometry. Yeah. So I think this is all. Thanks for watching.